Good morning, everyone. Myself, Dikshak SK. Now, I am going to talk about multiprocessor scheduling. Okay. Before we approach to this, we need to know about what is multiprocessor scheduling. Multiprocessor scheduling is nothing but more than one processor share the load to handle the execution of the process smoothly. Nothing but we are using more than one processor for scheduling the processors. In this multiprocessor scheduling, we are going to discuss about the four topics. They are approaches to multiprocessor scheduling, processor affinity, load balancing, and symmetric multithreading. Okay. There are two approaches in multiprocessor scheduling. The first approach is the multiprocessor system has all the scheduling decisions, input-output processing, and other system activities handled by a single processor. Here, nothing but there is one master server or a single processor which handles all the functions. Here, the other processor execute only user mode. This asymmetric multiprocessing is simple because only one processor accesses the system data structures and reducing the need for data sharing. And there is another approach here, symmetric. It is called as symmetric multiprocessing, where each processor is self-scheduling. All processors may be in common ready queue, or each processor may have its own private queue of ready processes. Regardless, scheduling proceeds by having the scheduler for each processor examine the ready queue and select the process to execute. Now talk about processor affinity. Consider what happens to cache memory when a process has been running on a specific processor. Then the data most recently accessed by the process populates the cache for the processor. As a result, successive memory accesses by the process are often satisfied in cache memory. Now, if the process migrates to another processor, the contents of cache memory must be invalidated for the processor being migrated from, and the cache for the processor being migrated to must be repopulated. Because of high cost of invalidating and repopulating caches, most symmetric multiprocessor systems try to avoid migration of process from one process to another and instead attempt to keep a process running on the same processor. This is known as processor affinity. It means nothing but a process of affinity for the processor on which it is currently running. Processor affinity can take several forms. When an operating system has a policy of attempting to keep a process running on the same processor but not guaranteeing that it will do so, we have a situation known as soft affinity. Here it is possible for process to migrate between the processors. Another type of processor affinity is hard affinity. Here, in some systems such as Linux, also provide system called hard affinity, thereby allowing a process to specify that it is not to migrate to another processors. Now let us talk about load balancing. On symmetric multiprocessing systems, it is important to keep the workload balanced among all the processors to fully utilize the benefits of having more than one processor. Otherwise, one or more processors may sit idle while other processors have high workloads along with list of processors awaiting the CPU. Load balancing attempts to keep the workload evenly distributed across all the processors in symmetric multiprocessing system. Load balancing is typically only necessary on systems where each process has its own private queue of eligible process to execute. On systems with a common run queue, load balancing is often unnecessary because once a processor becomes idle, it immediately extracts a runnable process from the common run queue. There are two general approaches to load balancing: push migration and pull migration. With push migration, a specific task periodically checks the load on each processor, and if it finds an imbalance, evenly distributes the load by moving processes from overload to idle or less busy processor. Pull migration occurs when an idle processor pulls a waiting task from the busy processor. Push and pull migration needs to be mutually exclusive and are in fact often implemented in parallel on load balancing systems. Symmetric multithreading. Symmetric multiprocessor system allows several threads to run concurrently by providing multiple physical processors. An alternative strategy is to provide multiple logical rather than physical processors. Such a strategy is known as symmetric multithreading, nothing but SMT. Here we can see that there is a common system bus and it is connected to physical CPU. And above that, we can see logical CPUs attached above the physical CPU. In the above figure, we can see that symmetric multithreading architecture with two physical processors, each housing two logical processors. From the operating system perspective, four processors are available for the work. Here we can see that there are two logical processors. They are physical. Here it is mentioned as physical CPU. It is the logical processor, and above that there are two other processors, combiningly four processors. The idea behind SMT is to create multiple logical processors on the same physical processor, presenting a view of several logical processors to the operating system, even on the system with only a single physical processor. Each logical processor has its own architectural state, which includes general purpose and machine state registers. Furthermore, each logical processor is responsible for its own interrupt handling, meaning that interrupts are delivered to and handled by logical processors rather than the physical ones. Otherwise, each logical processor shares the resource of its physical processor, such as cache memory and buses. Thank you.